Hey everybody, today we are going to start section 7.6, which is optimization problems. And I'm sure you guys are very excited to know that we're going to be doing a bunch of word problems in this section and learning how we can use calculus to solve some real world scenarios. So there are lots of problems where we need to find the maximum or the minimum value for functions. So that's where the word optimization comes from. The optimal solution is either going to be the maximum or the minimum, depending on the situation. And this solution is referred to as the optimum solution because it's maximum or minimum. The process is called optimization. So both of those being the biggest or the smallest, but in some way the maximum or the minimum. So remember when you take the derivative that the minimum or the maximum does not necessarily occur where the derivative equals 0 because you have to also look at the end point. And in these real world situations, it's important to consider the endpoints as well for whatever the situation is that you have. Okay, so to test for our optimal solutions, we're going to find the value where derivative is equal to 0. That's where most of our maximum or minimums are going to occur. And then we're going to make a sign diagram test. You could also do this, some of it graphically. Your calculator may or may not be very helpful for this because the graphs may be very large and go off the calculator. So the sign diagram test actually works out to be better for this usually. And for the IB test that we're going to have on this topic, that's what they're going to be mostly looking for. They're not going to be as interested in your ability to read a graph as they are in your ability to demonstrate calculus. Okay, so take a second and copy these down. You may have to pause the video so that you can get the steps. Step 1, the book actually says, if necessary, draw a clear diagram of the situation. I would say that that is always necessary. So the first thing you want to do is draw a picture most of the time. Some of the ones we're going to do today, a picture doesn't really do you any good, but most of the ones we do over the next couple days, you're going to want a picture of the geometry of the situation. You're going to figure out what formula you're going to use and the variable to be optimized, whether it's height or length or distance or radius or whatever it might be. And then you're going to write down any restrictions on that variable. So that's where your endpoints are going to come from those restrictions. You may also need some extra formulas. I'm going to add that in there. That's not in your book, but sometimes if you have, you're trying to maximize area, you might need to use perimeter. Sometimes if you're trying to maximize volume, you might need to use area. So there's some other formulas that you may need to pull in. The ones we're going to do today, most of the formulas are going to be given to you. That's why you don't necessarily need to draw the diagrams, but most of them you have to draw a diagram and then come up with the formulas on your own. So then once you have your formulas and you have your restrictions, you have any extra formulas, you've done any substitution you need to do, you're going to take the derivative and you're going to find the values of x where the derivative is equal to 0 because critical numbers are where most of our maximums and minimums occur. But then notice in step 4 that if there is a restricted domain, if there are some numbers that you can't go above or below, then the maximum or minimum may occur not necessarily at the derivative, but also at the endpoint. Then we're going to do a sign diagram test to verify that you have a maximum or a minimum. So take a minute, pause the video, get those things written down so that you have a series of steps to use, especially over the next couple days as we branch into some more difficult word problems. Okay, so here's our first one. And we're looking at a factory making X thousand chopsticks per day. And the cost of making those chopsticks is given to us. And also the selling price of the chopsticks. So we're going to use calculus to find the production level that maximizes profit. Okay, so look what we have here. We have cost and we have revenue, the amount of money that you're going to bring in, but the question is asking us about profit. So you might remember from things we have done before, profit equals revenue minus cost. So the first thing we're going to have to do is create a profit equation. Now, like I said in the last slide, this is not necessarily one that you're going to want to draw a picture for. This one's not geometric in nature, but you are going to have to do that most often. So revenue. Well, they tell us that each pack of 1,000 chopsticks sells for $28. That's where my revenue is going to come from. And then the cost is here. That's the cost, and X standing for 1,000 chopsticks. So you can see that the revenue is here, $28 for every 1,000 that you sell, and we're going to subtract the cost. Anytime you do this kind of thing, it's important that your cost function is in parentheses so that you can distribute your negative, combine like terms, and we're going to end up with this. Okay, so then from our directions that we had just a minute ago, we know the next thing that we want to do is find the derivative of this because we're going to be looking for maximum and minimum values. So I'm going to take the derivative of the profit function. All right, 2 times negative 0.4, negative 0.8x plus, and that's x to the first, so it's going to work out to be 26.4. Okay, then if I want to find the maximum or minimum value, I'm going to take that and I'm going to set it equal to 0. Try to make a better 8 on this one. All right, subtracting 26.4 from both sides. And then I'm going to divide both of those by 8. Let me pick up my calculator here. Let me divide by negative 0.8. So negative 26.4 divided by negative 0.8. And I get that x equals 33. So you might be tempted at this point just to say that the answer is 33. The production level that maximizes profit, I'm going to work with that 33. However, you always need to go back and test. You will not get full points on your paper 2 question, especially if you do not go back and test. And also just for the process as a whole, there was a story when I used to teach calculus years ago about the government creating a plane that would be undetectable by radar. And so the engineers did the derivative, they set it equal to 0, they found what they thought was the minimizing point, but they didn't actually test it. And so what they found was the maximizing point. They actually used our tax dollars to create the worst possible aircraft because they didn't take the time to go back and test. They just assumed that it was what they wanted. So we're going to go back and test that. I'm going to draw a little sign diagram here. Put 33. All right, so I am going to pick a value that's less than 33. The easiest one I can think of is 0. And if I put 0 into my derivative, so I'm substituting into the derivative, which is here. I put 0 in place of x. You can see I'm going to get 26.4, which is greater than 0. So my function is increasing. And then I'm going to pick a value larger than 33. Let's say 34. That's terrible looking, but let's go ahead and substitute that in there. So negative 0.8 times 34 plus 26.4. And I end up with negative 0.8, which is less than 0. So it's going down there. So my function is increasing and then decreasing, which means that 33 is in fact a maximum value. So X being 33 does not mean that the factory is going to make 33 chopsticks. It is unlikely they would make a lot of money off of 33 chopsticks. But I see right here that it's X thousand chopsticks. So the answer to the question, 33,000, and then determine the profit at that level. So if I'm trying to find the profit, at this point, I want to go back to my profit equation, which is here, and I'm going to put 33 in place of all those x's, so negative 0.4 times 33 squared, because the 1,000 is built into the equation, so I don't need to type that in. 26.4 times 33 minus 150, and I get $285.60. So the profit per day, $285.60. Okay, so if we go back and look at the original equation, the profit equation, which is here, I see that the leading coefficient is negative, which means it's a parabola opening down. Now, why does it make sense that the parabola would open downwards based on the words in this problem? Well, it's a maximizing question, so it makes sense that we would have a maximizing value. The vertex ought to be on top, and so it makes sense that the parabola would open downward in this particular situation. All right, let's try one more. I have again a cost function and a revenue function, and I want to find the maximum profit. So I remember from the last screen that profit equals revenue minus cost. So I'm going to substitute in, here's revenue, and I'm going to subtract away the cost. I'm going to remember to put my parentheses there so that I distribute the negative like I should. Okay, so let's see what we're going to have here. We're going to have 15x minus 4x, that's going to be 11x, and I'm going to have negative 0.002 x squared minus 0.02x squared, so that's going to be negative 0.022 x squared minus 720. So that's not in descending order, but it does have all the things that I need. I see the word maximize. Anytime I see the word maximize or minimize, my brain is automatically going to think derivative. I'm automatically going to think, hey, I better look for a critical number. So I'm going to take the derivative. Derivative of 11x is 11. 0.022 times 2, 0.044x. And the derivative of negative 720 is 0. All right, so I'm going to take that, set it equal to 0. So subtracting 11 from both sides. Oops, I put too many zeros. And then I'm going to divide. So negative 11 divided by negative 0.044. And I get 250. Okay, so again, I'm not going to assume that that 250 is what I want. I'm going to do a little sign diagram to make sure. So here's 250. All right, if I take a value that is less than 250, the easiest one is 0. And I substitute 0 into the derivative, so where I'm substituting is here. Putting 0 in place of that x, and I'm going to get 11, which is greater than 0, which means my function is increasing. All right, the next thing I need to do on the other side of 250, I need to substitute in a value larger than 250 into that derivative. Let's do 251. So I need my calculator for this one. 11 minus 0.044 times 251. And I get negative 0.044. It doesn't really matter what negative number I get. The important thing is that I got a negative number. And that means that my function is decreasing. So if it's increasing and then decreasing, 250 is in fact a maximum. So that is the answer that I want. X is going to be equal to 250. Okay, so this is just an introduction to optimization problems. We'll get into some more complicated ones over the next couple days. But for tonight, work on 7-6 worksheet numbers 1 through 3. Really think through these problems. Give your brain time to ponder through and understand so that when we do the more difficult problems tomorrow, you will have already had a day to kind of digest this, and tomorrow's problems will make more sense.